Origins of signal processing. Before the digital age reduced the world to a stream of binary digits, the processing of information was a physical, visceral endeavor. A signal was not an abstract mathematical sequence stored in a silicon memory cell. It was a tangible force of nature. It was the rise and fall of an electric current surging through a copper cable on the floor of the Atlantic Ocean. It was the mechanical rotation of a brass gear in a differential analyzer. It was the compression of air waves striking a concrete parabolic mirror on the coast of Kent. The history of signal processing is, at its fundamental level, the history of humanity's struggle to impose order on the chaos of the physical world. It is the story of how scientists and engineers learned to manipulate the fundamental properties of matter and energy, mass, momentum, capacitance, inductance, and resistance, to extract meaning from noise. This review explores the rich and complex origins of signal processing, tracing its evolution from the abstract mathematical theories of the Enlightenment to the electromechanical zenith of the Second World War. It is a narrative that spans centuries and disciplines, weaving together the insights of reclusive mathematicians, the ambitions of industrial monopolists, and the desperate ingenuity of nations at war. In this pre-digital era, the algorithm was a physical machine, and the computation was a continuous flow of voltage or torque. To understand modern digital signal processing, one must first understand these analog roots. For the fundamental theorems that govern today's wireless networks and artificial intelligence models were forged not in code, but in the fires of the analog age. Mathematical roots. Antiquity to the 19th century. The intellectual scaffolding of signal processing was erected long before the technology existed to implement it. The human desire to quantify and model the natural world led ancient mathematicians to develop methods of approximation that would eventually become the basis of sampling and quantization. As early as Antiquity, the method of exhaustion used by Archimedes to calculate the area of a circle treated the continuous curve as a polygon with an infinite number of discrete sides. This conceptual leap, viewing the continuous as a limit of the discrete, is the philosophical ancestor of the sampling theorem. However, the true mathematical language of signal processing began to take shape in the 17th and 18th centuries with the development of calculus and the study of planetary motion. Astronomers and surveyors were the first to grapple with the problem of noise. No two observations of a star's position or planetary orbit were ever identical due to atmospheric distortion and instrument error. The challenge was to extract the true signal from the noisy measurements. In the early 19th century, Carl Friedrich Gauss, the prince of mathematicians, formalized the treatment of error. While working on the orbital prediction of the dwarf planet Ceres, Gauss developed the method of least squares. He posited that errors in measurement were not random chaos, but followed a specific probabilistic distribution, the bell curve or Gaussian distribution. By minimizing the sum of the squares of the differences between observed values and a theoretical model, Gauss showed that one could mathematically estimate the most probable true value. This was a watershed moment. Gauss essentially defined the concept of estimation theory. He treated the observation as a composite entity, the signal, the truth, plus the noise, the error. The goal of mathematics was to filter out the noise to reveal the signal. This probabilistic approach would lie dormant for a century until it was resurrected by Norbert Wiener to solve the problem of anti-aircraft fire control. But the seed was planted. Information is not absolute, it is statistical. While Gauss dealt with error, Jean-Baptiste Joseph Fourier dealt with complexity. In 1822, Fourier published his magnum opus, Théorie analytique de la chaleur, the analytical theory of heat. His goal was to model the diffusion of heat through solid bodies, a physical process governed by partial differential equations. In the course of this work, Fourier made a startling claim that would become the cornerstone of all signal processing. Any continuous periodic function, no matter how complex or irregular, could be represented as the sum of simple sinusoidal waves. At the time, this idea was controversial. Prominent mathematicians like Lagrange were skeptical that a signal with sharp corners, like a square wave, could be constructed from smooth sine waves. Fourier insisted that with an infinite series of harmonics, the approximation would converge. He was right. The Fourier transform provided the bridge between the time domain, how a signal changes moment by moment, and the frequency domain, how much energy the signal contains at each frequency. Fourier's insight allowed engineers to deconstruct reality. A complex sound, like a chord played on a piano, or the vowel sound of a human voice, was not a monolithic entity. It was a recipe of frequencies. By adjusting the proportions of these ingredients, boosting the bass, cutting the treble, one could alter the signal's character. This was the birth of spectral analysis and filtering, concepts that would remain abstract until electricity provided a medium fluid enough to manipulate. While Fourier focused on periodic, steady-state signals, the real world is full of transients, sudden shocks, decaying pulses, and starting currents. Pierre-Simon Laplace, building on the work of Euler, developed a transform that extended Fourier's analysis to these transient phenomena. The Laplace transform mapped time domain functions into a complex frequency domain, the S-plane, allowing for algebraic solutions of differential equations. For the future electrical engineer, the Laplace transform was the key to stability. It provided a way to analyze how a system, whether a suspension bridge or a telephone amplifier, would react to a sudden disturbance, a step function. It could predict whether the system would settle down smoothly or oscillate wildly out of control. This mathematical tool would become essential in the design of feedback control systems and analog filters, serving as the rigorous proof behind the intuition of the circuit designer. Telegraphy and the tyranny of the medium. The transition from mathematical theory to engineering reality began in earnest with the electric telegraph. In the mid-19th century, the telegraph was the internet of its day, a Victorian internet that shrank the world from weeks to minutes. However, as telegraph lines grew longer, extending from city to city and eventually under the ocean, engineers encountered a phenomenon that defied the simple DC circuit theories of the time: signal distortion. On short landlines, a dot was a dot and a dash was a dash. The current turned on and off almost instantly. But on long submarine cables, the signal behaved differently. The sharp click sent from the transmitter arrived at the receiver as a long, slurred, lethargic rise in current. The dots and dashes blurred together into an unintelligible smear. This was the retardation of the signal, a problem that threatened to bankrupt the investors of the first transatlantic cable projects. The man who diagnosed this malady was William Thomson, later Lord Kelvin. In the 1850s, Thomson analyzed the submarine cable not as a simple wire, but as a massive capacitor. The copper conductor was the inner plate, the seawater was the outer plate, and the gutta-percha insulation was the dielectric. When a voltage was applied, the current could not simply flow to the other end. It first had to charge this immense distributed capacitance. Thomson applied Fourier's heat diffusion equations to the flow of electricity. He derived the law of squares, which stated that the time required for a signal to reach a detectable voltage at the far end was proportional to the square of the cable's length. A 2,000-mile cable was not twice as slow as a 1,000-mile cable. It was 4 times as slow. This theoretical barrier suggested that transoceanic communication might be impossibly slow. The controversy that followed, the Great Eastern Saga, was a battle between two philosophies of signal processing. On one side was Wildman Whitehouse, the project's chief electrician, a proponent of brute force. Whitehouse believed that if the signal was weak and distorted, the solution was to hit it harder. He constructed massive induction coils to blast the 1858 cable with thousands of volts. He treated the cable as a passive pipe that was clogged, attempting to force the fluid through by pressure. Conversely, Thomson advocated for signal conditioning and sensitivity. He understood that the information was still present in the smeared current, it just needed a detector capable of resolving it. Thomson invented the mirror galvanometer, a masterpiece of analog instrumentation. A tiny mirror was suspended by a single silk fiber inside a coil of wire. Even the faintest trickle of current from the Atlantic cable would cause the mirror to twist slightly. A beam of light reflected off the mirror onto a scale magnified this movement, allowing the operator to read the derivative of the signal, the initial rise of the current, rather than waiting for the full charge. The tragedy of the 1858 cable, its failure after only a few weeks of operation, was caused by Whitehouse's high-voltage pulses, which compromised the insulation. But the brief success of the cable, which carried Queen Victoria's 98-word message to President Buchanan, a transmission that took 16 hours, vindicated Thomson's theory. When the permanent cables were laid in 1866, they were operated according to Thomson's principles of low voltage and sensitive detection, establishing the first victory of signal theory over power engineering. While Thomson mastered the capacitive nature of the cable, he treated the signal essentially as a diffusion phenomenon, like heat. It was the reclusive and eccentric genius Oliver Heaviside who realized that electricity on a wire was a wave, governed by the laws of electromagnetism. Living in isolation and often at odds with the scientific establishment, Heaviside reformulated Maxwell's equations into the vector calculus form used today. In 1876, he derived the telegrapher's equations, which took into account not just resistance and capacitance, but also inductance and leakage. Heaviside discovered a counterintuitive truth. Inductance, usually seen as a source of resistance to changing current, was actually the cure for distortion. Heaviside proved that the distortion of a signal, the way different frequencies traveled at different speeds, dispersion, and attenuated at different rates, was caused by the imbalance between the magnetic and electric fields around the wire. He formulated the Heaviside condition. If the ratio of inductance to resistance equaled the ratio of capacitance to leakage, the line would be distortionless. On such a line, all frequencies would travel at the same speed and attenuate equally, preserving the shape of the voice or telegraph signal perfectly. Heaviside's solution was to load the line by adding inductance. This could be done by wrapping the wire in iron tape or by inserting coils at regular intervals. Heaviside, a man of pure science, published his findings but did not patent a practical device. Decades later, at the turn of the century, the implementation of this idea became a fiercely contested commercial prize. Michael Pupin, a Serbian-American physicist at Columbia University, patented a precise method of inserting these loading coils at calculated intervals along a telephone line in 1899. Pupin's analysis provided the engineering specifications that Heaviside's general theory lacked. The impact was immediate and lucrative. AT&T, desperate to extend the range of its telephone network without resorting to prohibitively expensive thick copper wires, purchased Pupin's patent. The sums involved were staggering for the time. Pupin received approximately $455,000, equivalent to over $11 million today. The loading coil saved AT&T an estimated $100 million in the first quarter of the 20th century. This episode highlighted a recurring theme in the history of signal processing: the lag between mathematical insight and engineering application. Heaviside's abstract vector calculus laid the groundwork, but it took Pupin's practical realization and AT&T's capital to turn the distortionless line into a reality that allowed human voices to travel between cities with clarity. Era of amplification and telephony. Passive components, resistors, capacitors, and inductors could shape a signal, filter it, and delay it, but they could not add energy to it. The passive era of signal processing reached its limit with the physical resistance of the wire. No matter how perfectly a line was loaded, the signal eventually faded into the thermal noise. The quest for a telephone repeater, a device that could rejuvenate a dying signal, led to the invention of the vacuum tube. In 1906, Lee de Forest added a third element, a zigzag wire grid, to the existing Fleming valve diode, creating the Audion triode. This device was the first electronic amplifier. By applying a weak, fluctuating voltage to the grid, de Forest could control a powerful stream of electrons flowing from the heated filament to the plate. It was a valve for electricity, allowing a small signal to modulate a large power source. The Audion was initially a mysterious and unreliable device. De Forest believed incorrectly that the presence of gas ions was essential to its operation. It was the researchers at Bell Labs and General Electric, including Irving Langmuir, who refined the device into the high-vacuum triode, a stable and predictable amplifier. By 1915, AT&T had installed these vacuum tube repeaters along a line stretching from New York to San Francisco, inaugurating transcontinental telephone service. For the first time, signal processing was active. The signal could be refreshed indefinitely, decoupling communication distance from signal energy. This opened the floodgates for complex processing chains. Signals could be amplified, inverted, mixed, and filtered without the catastrophic loss of power that plagued passive networks. With the ability to amplify signals came the desire to economize the medium. Copper wires were expensive to string across a continent. Telephone engineers realized that a single pair of wires had a bandwidth far exceeding what was needed for a single human voice, which requires only about 300 to 3400 Hz. This realization birthed frequency division multiplexing, FDM. By using the vacuum tube as an oscillator and mixer, engineers could shift the frequency of a voice signal. One conversation could be carried at its baseband frequencies. A second conversation could be modulated onto a carrier wave at 12 kHz, a third at 16 kHz, and so on. These stacked signals traveled together down the wire and were separated at the receiving end. The success of FDM depended entirely on the quality of the separation. This required filters of unprecedented precision. The crude resonant circuits of the radio pioneers were insufficient. They allowed crosstalk between adjacent channels. In 1915, George Campbell of Bell Labs and Carl Willy Wagner in Germany independently developed the theory of the wave filter. Using Heaviside's transmission line theory, they designed ladder networks of inductors and capacitors that could mathematically slice the frequency spectrum. They defined the concepts of passband, the frequencies to let through, and stopband, the frequencies to block. The design of these analog filters became a high art. Engineers used image parameter theory to cascade sections of filters, creating circuits with steep roll-offs that acted like brick walls in the frequency domain. These passive LC filters were the silent sentinels of the telecommunications network, sorting the cacophony of millions of voices into orderly lanes of traffic. The mathematical sophistication required to design these networks, involving complex impedance matching and hyperbolic functions, represented the pinnacle of pre-computer circuit theory. World War-era detection, radar, and sonar. The outbreak of the Second World War transformed signal processing from a commercial utility into a technology of existential survival. The need to detect enemy aircraft and submarines in the fog of war drove the development of entirely new theories of detection and estimation. Before the dominance of electromagnetic radar, nations experimented with acoustic detection. The most ambitious of these projects was the British network of sound mirrors, or listening ears. Built along the coasts of England, most notably at Denge in Kent, these were massive concrete structures, some standing 20 or 30 feet tall, shaped into precise parabolic or spherical sections. They functioned as acoustic telescopes. The hard concrete surface reflected incoming sound waves from enemy aircraft engines, focusing them to a focal point where a microphone or a human listener was stationed. The physics of the sound mirror was sound, pun intended, but its utility was doomed by the medium. Sound travels at approximately 340 meters per second. In the era of slow biplanes, this was sufficient, but as aircraft speeds increased in the 1930s, approaching 300 miles per hour, the latency of sound became fatal. By the time the sound of a bomber reached the mirror and the operator calculated a bearing, the aircraft was miles away from its apparent position. The sound mirrors were abandoned, standing today as silent concrete monuments to the limitations of analog processing speeds. A similar battle was being fought beneath the waves. The threat of the U-boat in WWI led to the development of ASDIC, Anti-Submarine Detection Investigation Committee, later known as Sonar. The breakthrough in sonar was the transducer. In 1917, Paul Langevin, a French physicist, utilized the piezoelectric effect discovered by the Curie brothers. He constructed a sandwich of quartz crystals between steel plates. When an electric pulse was applied, the quartz expanded, generating a high-frequency ultrasonic ping. When the echo returned, it compressed the quartz, generating a voltage. Sonar signal processing was a struggle against the complex acoustics of the ocean. The ocean is not a homogeneous medium. Layers of water at different temperatures, thermoclines, refract sound waves, creating shadow zones where submarines can hide. Early sonar operators had to be skilled signal processors, listening to the Doppler shift of the echo to determine if a submarine was approaching or retreating, and mentally filtering out the background noise of shrimp, whales, and waves. The limitations of acoustic detection led to the adoption of radio waves, which travel at the speed of light. This was the birth of radar, radio detection and ranging. Radar is, in essence, an active signal processing system. A transmitter sends out a known signal, a pulse, and a receiver looks for a reflection, an echo. The core challenge was the signal-to-noise ratio, SNR. The echo from a distant aircraft is infinitesimally weak, often buried in the thermal noise generated by the movement of electrons in the receiver's own vacuum tubes. The early radar systems, like the British Chain Home, used floodlight-style transmission and relied on operators to stare at an oscilloscope, an A-scope, picking out blips in the grass of noise. But as the war progressed, the need for automated and optimized detection became paramount. In 1943, Dwight North, a researcher at RCA Laboratories, wrote a classified report that revolutionized radar receiver design. He asked a fundamental question: what is the optimal filter to maximize the SNR of a received pulse in the presence of white noise? North proved mathematically that the best possible filter was one whose impulse response was the time-reversed and complex conjugate of the transmitted pulse. This became known as the matched filter, or North filter. The concept was profound. It meant that the receiver shouldn't just look for energy, it should look for the specific shape or pattern of the transmitted signal. A matched filter acts as a template matcher. It slides the memory of the transmitted pulse over the incoming noisy signal. When the two align, the output spikes to a maximum. In the analog domain, Implementing a perfect mathematical correlation was difficult. However, North showed that for a simple rectangular radar pulse, the matched filter could be approximated by a standard intermediate frequency bandpass filter with a specific bandwidth. This theoretical guidance allowed engineers to tune their radar sets for maximum range, effectively pulling targets out of the noise floor using math. Another plague of radar was clutter, strong reflections from stationary objects like mountains, buildings, or the sea surface. These static echoes often swamped the smaller echoes of moving aircraft. To solve this, engineers developed Moving Target Indication, or MTI. MTI exploits the Doppler effect. A moving target shifts the phase of the radio wave slightly from pulse to pulse. A stationary target returns the exact same phase every time. To detect this change, the radar needed memory. It needed to store the echo from pulse 1 and compare it to the echo from pulse 2. If the echo was identical, stationary, it was subtracted out. If it changed, moving, it was displayed. In the 1940s, there was no digital RAM to store the radar signal. The solution was the mercury delay line. This device consisted of a tube filled with liquid mercury with piezoelectric transducers at both ends. The electrical radar signal was converted into a sound wave, a mechanical vibration that traveled through the mercury. The length of the tube was precisely calibrated so that the travel time of the sound exactly matched the interval between radar pulses, typically a few milliseconds. The delayed pulse emerging from the mercury was then subtracted from the new incoming live pulse in a vacuum tube differential amplifier. The mountains canceled out, the planes remained. This delay line canceller was a triumph of hybrid signal processing, using the slow speed of sound in liquid metal to create a time buffer for the speed of light. Era of Prediction and Cybernetics. Signal processing in WW2 was not just about detection, it was about prediction and control. The problem of anti-aircraft fire control, hitting a fast-moving plane with a slow-moving shell, required solving differential equations in real time. The Bell Labs M9 gun director, deployed in 1943, was the pinnacle of electronic analog computing. Unlike previous mechanical directors that used cams and gears, the M9 used electricity to model mathematics. The M9 represented physical quantities, range, azimuth, elevation, as continuous voltages. It used op-amps, high-gain vacuum tube DC amplifiers, to perform mathematical operations. To integrate a function, the M9 charged a capacitor through a resistor. To differentiate, find velocity, it measured the current across a capacitor. The M9 closed the loop between the radar, sensor, and the gun, actuator. It took the radar data, calculated the velocity and acceleration of the target, computed the ballistic trajectory of the shell, and moved the gun to the predicted intercept point. The system was so effective that during the defense of London against the V-1 flying bombs, which flew straight, predictable paths, M9-directed batteries shot down over 90% of the targets in the final weeks of the campaign. While the M9 handled the ballistics, the theoretical problem of prediction was being tackled by Norbert Wiener at MIT. Wiener was asked to improve the tracking of aircraft that were not flying straight lines, but taking evasive action. Wiener realized that the pilot's motion was a stochastic or random process. It wasn't completely random, the pilot couldn't turn the plane instantly, but it wasn't fully deterministic either. It was a statistical time series. In 1942, Wiener produced a classified report titled The Extrapolation, Interpolation, and Smoothing of Stationary Time Series. Due to its yellow cover and the impenetrable difficulty of its mathematics, it was nicknamed the Yellow Peril. In this document, Wiener formulated the Wiener filter. Unlike the North filter, which optimized for a known pulse shape, The Wiener filter optimized for the statistical properties of the signal and the noise. Wiener framed the problem as minimizing the mean square error between the predicted position and the actual position. Wiener's work was a paradigm shift. He moved signal processing from the deterministic world of circuit design to the probabilistic world of information theory. He treated the signal as a carrier of information and noise as a corrupter of that information. His realization that the mathematics of control systems, machines, and the nervous systems, biology, were effectively the same led him to coin the term cybernetics. The Yellow Peril laid the foundation for modern estimation theory, influencing everything from communications engineering to the Kalman filters used in space navigation. Analog computing, the mechanical brains. Before the transistor, computer often referred to a machine that modeled physics using mechanical analogies. These machines were the heavy lifters of signal processing before the digital dawn. One of the earliest and most beautiful analog computers was Lord Kelvin's tide predicting machine, developed in the 1870s. Tides are complex waveforms created by the gravitational pull of the moon and sun, composed of many overlapping periodic cycles or harmonics. Kelvin's machine was a mechanical Fourier synthesizer. It used a system of wires and pulleys. Each pulley oscillated up and down at a frequency corresponding to a specific tidal constituent, like the lunar semi-diurnal cycle. A single wire ran over all the pulleys, physically summing their vertical motions. The resulting movement drove a pen on a rotating drum, drawing the predicted tide curve for any port in the world for a year in advance. This machine processed signals by literally adding them together with steel and wire. In the 1930s, Vannevar Bush at MIT constructed the differential analyzer, a room-sized mechanical computer designed to solve differential equations that were too complex for manual calculus. The heart of the machine was the ball and disc integrator. A horizontal disc rotated at a speed representing an independent variable, like time. A heavy steel ball rested on the disc, driven by friction. The distance of the ball from the center of the disc represented the variable to be integrated. As the disc spun, it turned the ball, which in turn rotated a cylinder. The total rotation of the cylinder represented the integral of the function. The machine's power came from its ability to chain these integrators together. The output of one integration could be the input to another, allowing for the solution of second-order and third-order differential equations. The engineering miracle that made this possible was the torque amplifier, invented by Henry Niemann. The torque drive of the ball and disc was incredibly weak. It couldn't turn the heavy gears of the next stage without slipping. The torque amplifier used a capstan principle, similar to a ship's winch. The weak output shaft tightened a string wrapped around a powerful rotating drum. The friction of the string against the drum grabbed the output shaft and turned it with massive force. The differential analyzer was the supercomputer of its day. It was used to calculate ballistics tables for the Army and radar propagation curves for the MIT Radiation Lab. Yet it was a temperamental beast. Programming it meant using wrenches and screwdrivers to rearrange gear trains. A calculation could take days to set up. Its precision was limited by the mechanical slippage of the balls and the stretching of the torque amplifier strings. Yet it demonstrated that computation was a physical process that could simulate the differential equations of the universe. Pre-digital digital, security and synthesis. In 1943, the Allies deployed SIG-SALLY, a secure voice system connecting Washington, London, and later other command centers. It was the first system to enable secure conversations between Winston Churchill and Franklin Roosevelt. SIG-SALLY was an analog machine that functioned digitally. It occupied a large room, weighed 55 tons and used thousands of vacuum tubes. To secure the voice, Sig-Sally first used a vocoder, or voice coder. It did not transmit the voice waveform directly. Instead, it analyzed the voice into 10 frequency bands and a pitch signal, measuring the energy in each band every 20 milliseconds. This was a form of signal compression. Crucially, Sig-Sally then quantized these energy levels. It rounded the continuous voltage of each band to one of 6 discrete steps. This was the first practical use of pulse code modulation, or PCM. To encrypt the signal, the system added a one-time pad key to the quantized values. This key was a stream of random noise generated by the thermal fluctuations of a vacuum tube, a truly random physical source. The noise was recorded onto phonograph records. Identical records were flown to both ends of the link. The transmitter added the noise to the voice, modulo 6. The receiver, playing the synchronized record, subtracted the noise to recover the voice. The system was nicknamed the Green Hornet because of the buzzing control tones heard on the line. Sig-Sally proved that a continuous analog signal, voice, could be broken down into parameters, quantized into digits, encrypted with math, and reconstructed synthetically. It was the grandfather of every secure digital phone and voice-over IP system in use today. While Sig-Sally secured the content of the message, another invention sought to secure the transmission path itself. In 1941, Hollywood actress Hedy Lamarr and avant-garde composer George Antel received a patent for a secret communication system intended for radio-guided torpedoes. The problem was jamming. A simple radio guidance signal on a single frequency could be easily blocked by the enemy broadcasting noise on that channel. Lamarr's idea was frequency hopping. She proposed that the transmitter and the torpedo should rapidly switch frequencies in a synchronized pseudo-random pattern. To an enemy listener, the signal would appear as fleeting, unpredictable bursts of noise scattered across the spectrum, making it impossible to jam. To achieve synchronization, Antel suggested using the technology of the player piano. Miniature paper rolls, perforated with the hopping code, would turn inside the torpedo and the controlling ship. The mechanism would use 88 frequencies, matching the 88 keys of a piano. Although the U.S. Navy rejected the idea during the war as too mechanically cumbersome, fearing the paper rolls would jam in a torpedo, the concept of spread spectrum was later resurrected. In the 1950s, with the advent of transistors, frequency hopping became feasible. It became the basis for secure military communications and eventually the underlying technology for modern consumer wireless standards like Bluetooth and Wi-Fi. Lamarr's intuitive leap, trading bandwidth for robustness, was a fundamental insight of modern signal theory. Digital Revolution and Modern Architectures, 1948 to present. The history of technological progress in the post-war era is, at its core, a history of translation. It is the story of humanity learning to translate the continuous, infinite, and messy fluctuations of the physical world, the vibration of a vocal cord, the scattering of light photons, the propagation of radio waves, into the discrete, orderly, and finite language of mathematics. This translation, the paradigm shift from analog to digital, was not merely a change in storage formats or transmission cables. It was a fundamental restructuring of how civilization processes reality. At the heart of this transformation lies the discipline of digital signal processing, DSP. It is a field that sits at the uncomfortable intersection of abstract mathematics, semiconductor physics, and information theory. For decades, it remained an arcane subdiscipline of electrical engineering, hidden inside military radar bunkers and university mainframes. Yet, as the decades passed, DSP migrated from the laboratory to the living room and eventually to the pocket of nearly every human being on the planet. This second part traces that evolutionary arc, exploring the theoretical origins in the 1940s, the algorithmic breakthroughs of the 1960s, the silicon explosion of the 1980s, and the contemporary rise of artificial intelligence as the new engine of signal processing. It argues that we have passed through three distinct epochs: the era of hardware-defined processing, where functions were wired into circuits; the era of software-defined processing, where general-purpose chips executed human-written algorithms; and the emerging era of data-defined processing, where neural networks learn to interpret signals in ways their creators never explicitly programmed. The information age begins. The digital world did not begin with a microchip, it began with a paper. In 1948, the United States was transitioning from a war economy to a consumer boom, and the telecommunications network was expanding rapidly. However, the systems of the day were fundamentally analog. Long-distance phone calls were plagued by noise. The farther a signal traveled, the more it degraded, accumulating static that could never be fully removed. Engineers viewed information as a vague, qualitative concept, much like meaning or intent. Shannon, a mathematician and engineer working at Bell Labs, changed this forever with the publication of A Mathematical Theory of Communication. Shannon realized that information was not abstract, it was a physical quantity that could be measured, quantified, and manipulated, much like mass or energy. He termed this quantity entropy, a measure of the uncertainty or surprise contained in a message. Shannon's work laid the theoretical foundation for digitization by decoupling the message from the medium. In an analog system, the signal is the message. If the voltage representing a voice fluctuates, the voice distorts. Shannon demonstrated that if a message could be encoded into symbols, it could be transmitted error-free over a noisy channel, provided the transmission rate did not exceed the channel capacity. This was a radical departure from the engineering wisdom of the time, which held that reducing noise required increasing power. Shannon showed that one could use coding. While Shannon provided the architecture for digital communication, a fundamental practical problem remained. The world is analog. Sound waves, light intensity, and temperature voltages are continuous functions of time. To process them digitally, they must be sampled, measured at discrete intervals. Common intuition in the 1940s suggested that this chopping process must inevitably destroy information. If you measure a sound wave at 1201 and again at 1202, what happens to the sound that occurred at 1201.5? Is it lost forever? The answer, provided by the Nyquist-Shannon sampling theorem, was a mathematical miracle that underpinned the entire digital revolution. Building on earlier insights by Harry Nyquist in 1928, Shannon proved that a continuous signal could be perfectly reconstructed from its discrete samples without any loss of information, provided one specific condition was met. The sampling rate must be strictly greater than twice the highest frequency component of the signal. This threshold, known as the Nyquist rate, implies that the spaces between samples do not contain hidden information, assuming the signal is band-limited. For example, the human ear can generally hear frequencies up to 20,000 Hz. In accordance with the theorem, if an audio signal is sampled at more than 40,000 times per second, the resulting stream of numbers captures everything a human can physically hear. The discrete points are sufficient to mathematically recreate the infinite continuous curve of the original sound wave. This theorem gave engineers the mathematical confidence to abandon continuous analog storage media, like vinyl records and magnetic tape, in favor of digital formats. However, the theorem also introduced a dangerous artifact known as aliasing. If a signal is undersampled, measured slower than the Nyquist rate, the high-frequency information does not simply vanish, it disguises itself as lower-frequency information. A classic visual analogy is the wagon wheel effect seen in Western films. A movie camera captures images at 24 frames per second. If a wagon wheel spins at a rate that aligns with this sampling frequency, the spokes may appear to stand still or even rotate backward. The camera is undersampling the motion, creating a false or aliased low-frequency representation of the high-speed rotation. In audio, this manifests as high-pitched signals folding over into the audible range as dissonant metallic distortion. To prevent this, every digital system must employ strict anti-aliasing filters to brutally sever any frequencies above the Nyquist limit before digitization begins. FFT revolution, the algorithm that sped up the world. For nearly 2 decades after Shannon's paper, digital signal processing was largely a theoretical exercise. The mathematics worked, but the economics did not. Processing a signal required transforming it from the time domain, a sequence of samples, to the frequency domain, a spectrum of sine waves, a task performed using the discrete Fourier transform, DFT. The DFT was computationally punishing. To analyze a signal with n data points, the algorithm required n-squared complex operations. For a modest dataset of 1,000 points, a computer had to perform 1 million operations. In the era of vacuum tubes and punch cards, this exponential scaling made real-time signal processing a fantasy. The geopolitical climate of the 1960s changed the equation. The Cold War was at its height, and the United States and the Soviet Union were engaged in a nuclear arms race. Following the Partial Test Ban Treaty of 1963, which banned atmospheric nuclear tests, the superpowers moved their testing underground. The only way to monitor compliance was to listen to the Earth itself. Seismographs and acoustic sensors generated rivers of data that needed to be analyzed for the spectral signatures of nuclear detonations, which differed distinctly from natural earthquakes. The urgency of national security demanded a faster way to compute the Fourier transform. The solution arrived in 1965, not from a weapons laboratory, but from a collaboration between James Cooley of IBM and John Tukey of Princeton. Tukey, a brilliant statistician who is also credited with coining the term bit, suggested a mathematical shortcut to Cooley during a brainstorming session. Cooley implemented the idea on an IBM 7094 mainframe. The resulting paper, an algorithm for the machine calculation of complex Fourier series, described what is now known as the fast Fourier transform, FFT. The FFT was not merely an optimization, it was an algorithmic paradigm shift. It reduced the computational complexity from n squared to n log n. For small datasets, the difference was negligible, but for the large datasets required in seismic monitoring or radar, the difference was astronomical. For a signal with 4,096 data points, a standard DFT requires roughly 16 million operations. The FFT requires only about 49,000. This is a speed-up factor of over 300. As n grows, the advantage becomes even more extreme. This logarithmic collapse of processing time meant that tasks which previously took hours of mainframe time could now be completed in seconds. The mechanism behind the FFT is a strategy of divide and conquer. The algorithm exploits the symmetry of the complex roots of unity, the sine and cosine values used in the transformation. It recursively breaks a large DFT into smaller DFTs. If the number of samples is even, the dataset is split into 2 halves, one containing the even-indexed samples and one containing the odd-indexed samples. These halves are processed separately and then recombined using a butterfly operation, a data flow diagram that resembles a pair of wings. This splitting continues until the problem is reduced to the simplest possible unit, a two-point transform. By reusing calculations rather than recomputing them, the FFT eliminates vast amounts of redundant arithmetic. Historical scholarship later revealed a fascinating twist. The FFT was not actually new. The great mathematician Carl Friedrich Gauss had derived the same algorithm in 1805, predating Fourier's own work on harmonic analysis, to calculate the orbits of Pallas and Juno. Gauss wrote his findings in Latin in a notebook that was not widely analyzed until the late 20th century. Thus, the algorithm that powers the digital age is actually an artifact of the Napoleonic era, rediscovered to police the atomic age. The immediate beneficiary of the FFT was the military. Radar systems operate by transmitting radio pulses and analyzing the reflections, echoes, from targets. To determine the speed of an incoming aircraft or missile, radar relies on the Doppler effect, the slight shift in frequency of the reflected wave caused by the target's motion. In the analog era, distinguishing a moving jet from a stationary mountain, clutter, was difficult and imprecise. With the FFT, radar systems could digitize the returning pulses and instantly transform them into the frequency domain. In this domain, stationary objects appeared at the center frequency, zero Doppler shift, while moving targets appeared as distinct spikes shifted away from the center. This processing, known as pulse Doppler radar, allowed for look-down, shoot-down capabilities, where an aircraft could detect low-flying targets against the clutter of the ground. The FFT allowed this analysis to happen in real time, scanning thousands of range bins and velocity gates simultaneously. Similarly, in Sonar, the FFT allowed submarines to analyze the acoustic spectrum of the ocean with high precision. Every ship and submarine emits a unique acoustic signature, a fingerprint created by the rotation of its propeller, the hum of its generator, and the vibration of its hull. By applying the FFT to hydrophone data, sonar operators could decompose the cacophony of the ocean into discrete frequencies, identifying the specific 60 Hz hum of a specific class of enemy submarine miles away. The FFT effectively gave eyes to the blind, turning sound into a visual map of the environment. Hardware evolution, the rise of the DSP chip. While the FFT provided the software roadmap, the hardware of the 1960s and 70s was ill-equipped to travel it. General-purpose microprocessors, CPUs, were designed for logic, control flow, and data movement, the tasks needed to run an operating system or a word processor. They were not designed for the relentless arithmetic of signal processing. DSP algorithms are fundamentally different from general computing. They are characterized by a single repetitive operation, the dot product. Whether filtering a signal, computing an FFT, or correlating two sequences, the processor must multiply a data sample by a coefficient and add the result to a running total. This is known as the multiply-accumulate operation. On a standard microprocessor of the late 1970s, a multiplication was a slow, multi-cycle ordeal implemented in microcode. Doing millions of them per second for real-time audio was impossible. The semiconductor industry responded by creating a new class of microprocessor, the digital signal processor, DSP. The race began in earnest in 1979, when Bell Labs introduced the DSP-1. This pioneering chip was not sold to the public, but was crucial for AT&T's telecommunications network. It was designed to handle the complex filtering required for the #1 electronic switching system, 1ESS, and its successors. The DSP-1 allowed the phone network to transition from electromechanical relays to digital switching, significantly increasing reliability and call capacity. However, the chip that truly defined the era was the TMS-3210, released by Texas Instruments in 1982. Often considered the Model T of the DSP world, the TMS-3210 brought high-speed signal processing to the mass market. Its success lay in its architecture. Standard computers use a von Neumann architecture, where program instructions and data share the same memory and the same bus. This creates a bottleneck. The CPU cannot fetch the next instruction and the data it needs at the same time. TI engineers utilized a modified Harvard architecture for the TMS-3210. This design separates program memory from data memory, providing each with its own bus. This allowed the chip to fetch an instruction, e.g., multiply, and the data, the numbers to be multiplied, in a single clock cycle. Furthermore, the chip included a dedicated hardware multiplier, a massive circuit on the silicon die committed solely to math. This allowed the TMS-3210 to perform a multiply-accumulate operation in just 200 nanoseconds. This speed was revolutionary, enabling applications that were previously the domain of supercomputers to be performed by a $500 chip. The success of the TMS-32 series triggered an arms race in the semiconductor industry. Competitors like Motorola with the DSP 56000 series and analog devices with the ADSP 2100 and Shark families entered the fray. A major divide emerged between fixed-point and floating-point processors. Fixed-point DSPs, like the early TI chips, represent numbers as integers. They are fast, cheap, and power-efficient, but they suffer from limited dynamic range. If a calculation results in a number larger than the register can hold, it overflows, causing catastrophic distortion. Programmers had to painstakingly scale their numbers to avoid this. Floating-point DSPs, like Analog Devices' Shark chips, represent numbers in scientific notation, automatically handling the decimal point. This offers vast dynamic range and easier programming, but requires more transistors, costing more and consuming more power. The industry bifurcated. Fixed-point chips went into cost-sensitive consumer devices like toys and mobile phones, while floating-point chips dominated high-end professional audio, medical imaging, and military radar. The availability of cheap, high-speed DSP chips in the 1980s and 90s catalyzed a revolution in consumer electronics. The abstract theories of Shannon and the algorithms of Cooley and Tukey were finally etched into silicon. The compact disc, CD, launched in 1982, was the first digital product to reach the mass consumer. It was a joint development by Sony and Philips, but the two giants had a technical disagreement. Sony, with its advanced semiconductor capabilities, had a 16-bit digital-to-analog converter ready for production. Philips, however, only had a 14-bit DAC, the TDA-1540. In the binary world, 2 bits is a massive difference. 16 bits offers 4 times the resolution of 14 bits. It seemed Philips would launch an inferior player. Philips engineers solved this hardware problem with DSP. They utilized a technique called oversampling. Instead of feeding the 14-bit DAC at the standard 44.1 kHz rate, they programmed a digital filter chip, the SAA7030, to feed the DAC 4 times faster, 176.4 kHz. By distributing the quantization noise over a wider frequency bandwidth and then filtering out the ultrasonic noise, they achieved a signal-to-noise ratio in the audible band that was equivalent to a true 16-bit system. This was a pivotal moment. It proved that smart signal processing could compensate for inferior analog hardware. The Philips CD100, despite its weaker DAC, was lauded for its sound quality, often described as warmer than the Sony counterparts, which used brick wall analog filters. Digital media is fragile. A scratch on a vinyl record causes a pop. A scratch on a CD destroys megabytes of data. To make the CD viable, engineers implemented cross-interleaved Reed-Solomon coding, CIRC. This is a heavy DSP workload. The data on a CD is not written sequentially, it is scattered, interleaved across the disk surface. When the laser reads the disk, the DSP de-interleaves the data and uses redundant parity bits to mathematically reconstruct any missing information. A CD player essentially solves a massive system of linear equations in real time as you listen to music. Without the DSP power to run Reed-Solomon algorithms, the optical disc format would have been practically unusable due to its susceptibility to minor physical defects. The second great triumph of the DSP chip was the GSM mobile phone standard. In the analog cellular era, 1G, each user occupied a dedicated frequency channel. This severely limited the number of users a cell tower could support. Digital 2G GSM needed to fit more users into the same bandwidth. The solution was compression. The human voice produces a lot of redundant data. The GSM standard utilized a DSP algorithm called linear predictive coding, LPC. Instead of transmitting the sound of the voice directly, LPC analyzes the voice to estimate the shape of the speaker's vocal tract, throat and mouth, and the excitation signal, air from the lungs. The phone transmits these parameters rather than the audio itself. The receiving phone's DSP then uses these parameters to synthesize a synthetic voice that sounds like the speaker. This reduced the data rate from 64 kilobits per second, standard telephone quality, to just 13 kilobits per second, allowing network operators to pack 5 times as many users onto the network. The DSP chip inside the Nokia and Motorola bricks of the 1990s was the engine of the mobile revolution. In the late 1990s, the internet arrived, but bandwidth was scarce. Transmitting raw CD audio 1.4 megabits per second was impossible. The Moving Picture Experts Group, MPEG, developed the MP3 standard to solve this. Unlike zip compression, which is lossless, MP3 is lossy. It throws information away. But it does so intelligently, using a psychoacoustic model. The DSP running an MP3 encoder analyzes the audio using a modified discrete cosine transform, MDCT. It looks for masking events. For example, if a loud snare drum hit occurs, the human ear is temporarily deaf to softer sounds immediately following it, temporal masking. Similarly, a loud tone at 1000 Hz renders the ear insensitive to a quiet tone at 1010 Hz, simultaneous masking. The DSP identifies these invisible sounds and deletes them from the data stream. It allocates bits only to the sounds the brain actually perceives. This allowed MP3 to reduce file sizes by 90% while maintaining acceptable quality. The explosion of portable MP3 players, and later the iPod, was driven by the availability of low-power DSPs capable of decoding these complex mathematical streams. Software and AI integration. The shift to defined radio and neural processing. As the 20th century dawned, the rigid coupling between hardware and function began to dissolve. In the 20th century, a radio was a collection of specific resistors, capacitors, and inductors soldered together to resonate at a specific frequency. To change the radio from AM to FM, or to a new military frequency, you had to physically rebuild the circuit. The new millennium brought the concept of virtualizing the hardware itself. The concept of software-defined radio, or SDR, proposes a radical simplification. Digitize the signal as close to the antenna as possible and do everything else in software. In an ideal SDR, the hardware is merely a generic dumb pipe that captures the entire radio spectrum, and the tuner, filter, and demodulator are just lines of code running on a processor. The military, burdened by a logistical nightmare of incompatible radios for different branches and allies, pioneered this technology. The seminal project was Speakeasy, initiated by the U.S. military in the early 1990s. The goal was to build a single radio unit that could emulate 10 different existing military waveforms, from HF to VHF to satellite links, simply by loading different software modules. The processing requirements were immense. The Speakeasy Phase 1 demonstrator used banks of the fastest TI DSPs available, the TMS-320C40, and occupied a rack large enough to fill the back of a cargo truck. It was not portable, but it proved the point. The radio had become code. As bandwidths increased from kilohertz voice to megahertz video data, standard DSP chips could not keep up. The industry turned to field programmable gate arrays, or FPGAs. An FPGA is a chameleon chip. Unlike a standard processor with a fixed instruction set, an FPGA consists of a sea of uncommitted logic gates that can be rewired electronically. An engineer can write code in languages like VHDL or Verilog that reconfigures the chip's internal circuitry to become a custom parallel processor. In modern 5G base stations, FPGAs are the workhorses. They handle the massive parallel streams of data from MIMO antennas, performing billions of operations per second with a latency measured in microseconds. They offer the speed of custom hardware with the flexibility of software updates. Simultaneously, the graphics processing unit, GPU, created for video games, evolved into a scientific instrument. NVIDIA's release of CUDA, Compute Unified Architecture, in 2007 allowed engineers to access the thousands of parallel cores in a graphics card for non-graphical tasks. In fields like synthetic aperture radar, or SAR, where an image is constructed from millions of radar pulses, GPUs proved superior to both DSPs and FPGAs. They offered massive floating point throughput and were easier to program than FPGAs. Today, the signal processing backend of many advanced radar and sonar systems is essentially a gaming supercomputer. We are currently witnessing the third and perhaps most disruptive phase of this history. We have moved from hardware-defined, analog, to software-defined, algorithms written by humans, to data-defined, algorithms learned by machines. For decades, signal processing relied on handcrafted features. In image processing, engineers spent years designing mathematical filters to detect edges, so Bell filters, or identifying key points, SIFT and HOG algorithms, to recognize objects. These algorithms were robust but rigid. They could only see what the engineer told them to look for. In 2012, a convolutional neural network named AlexNet shattered this paradigm by winning the ImageNet competition. AlexNet did not use handcrafted filters. It learned its own filters by looking at millions of images. It discovered that edges are important in the first layer, shapes in the second, and textures in the third. The engineer was no longer designing the signal processing pipeline. The engineer was designing the architecture that learned the pipeline. This revolution has spread to audio and wireless communications. In speech synthesis, traditionally, systems relied on vocoders, parametric models of the human voice derived from the LPC research of the 1960s. These systems sounded intelligible but robotic because the mathematical model was a simplified approximation of reality. In 2016, DeepMind introduced WaveNet, a generative neural network that synthesizes audio sample by sample. WaveNet does not know what a vocal tract is. It does not know about sine waves or formants. It uses a dilated causal convolution architecture to look at thousands of previous audio samples and predict the probability of the next sample. It learns the physics of air pressure waves directly from raw audio data. The result is a voice that captures the breaths, the lip smacks and the subtle intonations of a human speaker, nuances that no human engineer could ever write an equation for. While the original WaveNet was too slow for real-time use, successor architectures like parallel waveGAN have optimized this process, allowing your smartphone assistant to speak with a neural voice generated in real time. In the wireless world, researchers are now proposing to replace the fundamental mathematical blocks of communication, the channel estimator and the equalizer, with neural networks. The Deep RX concept uses deep learning to interpret the distorted radio signals received by an antenna. In traditional engineering, we model the channel mathematically, example Rayleigh fading, and design an inverter. A neural network, however, can handle the nonlinearities and chaos of real-world interference better than linear mathematical models. Some research suggests that 6G networks might use autoencoders, where the transmitter and receiver are two halves of a neural network that jointly learn a modulation scheme perfectly optimized for the specific environment they are in, inventing a new language of radio waves on the fly that no human designed. The journey from 1948 to the present is a narrative of increasing abstraction. Shannon gave us the bit, detaching information from the physical world. Cooley and Tukey gave us the FFT, detaching processing speed from the linear flow of time. The DSP chip designers gave us the hardware to decouple function from fixed circuitry. And now, the pioneers of deep learning are detaching the algorithm from the human programmer. We stand at a unique threshold. For 70 years, signal processing was a deductive science. We started with first principles, physics, math, and deduced the solution. We are now entering an inductive era. We start with the data and induce the solution. The anti-aliasing filters, the Fourier transforms, and the error-correcting codes that built the modern world are not disappearing, but they are being subsumed into a larger, more opaque, and infinitely more capable intelligence. The digital revolution digitized the signal. The neural revolution is digitizing the intuition.